Going to wrap things up with homework 10 today, and then we're going to embark upon chapter 9, which is about finite state machine minimization. I hope you had a chance to take a look at it. This is probably one of the more challenging chapters in the book. First, I would like to know if anyone had any specific questions about homework number 10. I think we kind of beat that one to death. And hopefully you are all well ahead of the game here on homework 10. Any questions? All right then. Seeing none, I'm going to move on to homework number 11, and that would be in chapter 9 of the book. And what you're going to do... what's your question? Question 7 in homework number 10. Let me get homework 10 out. So here's homework 10. Let's take a look and see what question 7 has in store for us. Okay, so question 7 asks, let's see if we can get this. What are the maximum number of states in a finite state diagram when you have a Moore machine with 5 flip-flops? How does one approach that problem? Well, let's assume for the moment that a Moore machine has 2 flip-flops, an A and a B. How many states can you have? 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 2, 3. Looks like I can have 4 states. So if I have 2 flip-flops, I can have 4 states because 2 to the 2 is equal to 4. So if somebody says, okay, now you have 5 flip-flops, then it's 2 to the 5, which must be equal to 32. And so that's how I would approach that problem. And in fact, when I look at the answer, indeed, it is 32. So that's a correct answer, and that is a good approach to the problem. What do you think of that? Is that good? Correct. That is correct, because the only thing that can determine the number of states is really the number of flip-flops. It doesn't matter. Yeah, I mean, inputs will certainly cause transitions. Outputs can be, well, you could have 16 outputs, right? I mean, let's think about this. If you have, well, let's see. Suppose you had an A and a B bit going in. You could easily have 4 outputs from a decoder, but you could have even more than that if you decide to, I don't know, come up with some more creative ways in which to take the different outputs and make other outputs. So the number of outputs doesn't matter. In fact, if one were to draw the diagram of the combinational logic block that has inputs going into a state register that then has some other combinational logic for output, that could have lots and lots of outputs, tons of outputs, but the number of states will be fixed by the number of flip-flops in the state register. So the number of outputs in here has nothing to do whatever, almost, with the number of states. It just almost doesn't matter. I guess one could make a compelling argument that you could have an infinite number of bits for output and still only have 4 states with 2 flip-flops. Any other questions about homework number 10? Can we do number 15 and 16, somebody writes. Okay, let's do that. Number 15. 15. This is a serial adder. So what happens with the serial adder is you have, and this is kind of like a picture, right? So we gotta show the picture. Right, here's the picture. It appears we can add an infinite number of bits with just one adder. So here's the adder, and here's the shift register, right? And what is it doing? Well, it's shifting the bits in, and this is adding one bit at a time. If you think about it, A and B can form a truth table, 0, 0, 0, 1, 1, 0, 1, 1, and the output is a sum and a carry. And the sum is the exclusive OR, 0, 1, 1, 0, and the carry outputs like this. This is assuming a half adder. So all you have to do is shift the bits in and then get the carry out to come back to the carry in at a later time. So if you want to do this with a carry in for the next stage, you write the same thing only with a carry in. And then you have A, B, carry in with a sum and a carry out. And now you can see how the sum is going to be 0, 1, 1, 0, 1, 0, 0, 1. And the carry out, there's going to be a carry out only when you have it here, and here, and here, and here. So now you have to create, the combinational logic in this full adder, which implements that truth table. And then, as the bits come in, you have to take, instead of having, like we saw in prior classes, a large array of flip-flops, full flip-flops, what we'll do is we'll just reuse this flip-flop and just keep cycling the carry out to the carry in after one delay with the D flip-flop. So the answer is true as long as you have enough carries. And I also had everybody watch the video on the ENIAC. I hope you had a chance to watch that. And that showed you a machine which was a general-purpose electronic digital computer made in 1945. And that machine, 80-year-old machine, used tubes. And it used a serial adder just like this, in design anyway, or in principle. It used BCD instead of binary, but other than that, it was the same principle. And so when you look at the adder that I presented to the class, it was implementing just this sort of thing. And that is that is something you can do to reuse the flip-flop, but it costs you, right? So in other words, you're trading space for time. This is a common theme in computer science. Here we're taking more time to do our addition. In other words, if there's 10 bits, we're going to take 10 times longer than if there's just one bit. But we traded off for hardware. Now we only need one D flip-flop and the combinational logic for a full adder that implements this truth table. If you can keep the bits coming in, you can keep adding them. And you can do that indefinitely. So that's a true statement. It's a serial adder. And you can do the same thing with serial multiply and serial divide, but that's beyond the scope of this homework. Someone said, can we do 16? Well, 16 is the same question, only recast differently. Now what we're doing is we're looking at the inputs. If a, b equals 0, and then s equals 0. If a, b equals 1, then s equals 1. And in fact, if you look at this particular truth table, that's exactly what we're seeing right in through here. And so the answer to that one is also true. You can build a full adder with a single D flip-flop. And in fact, if you look at the prior question, yes, we built a full adder with a single D flip-flop, and it can take an infinite number of bits. And so that's the answer to both 15 and 16. The two questions are linked together. I don't know if if you look at this diagram and then you look at 16, you can see the implementation that is being spoken about here in 15. And also, if you looked at the ENIAC video, you can see the tube implementation. Hope that answered your question. But then here comes another one. Can we go over question 8 as well? Yes, sure. We can do question 8. Absolutely. All right, so question 8 says, question 8 says, Moore machines. Suppose you were told that a Moore machine has 5 flip-flops and 3 inputs and 9 outputs. What are the minimum and maximum number of transition arrows starting at a particular state? Transition arrows. Now, those are different than the number of states, right? That's a whole different question. So what do we know? We have 5 flip-flops. Okay. 1, 2, 3, 4, 5. And then somebody says something like, there are 3 inputs, A, B, C, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 0, 1, 1, 1. Number of the inputs, 0, 1, 2, 3, 4, 5, 6, 7. So that's 8. So that means that any one of these inputs can cause a transition. And if everybody goes back to S0 for every input, then you could have 8 inputs coming in to here for all the different values, the 8 different values for the 3 bits. And then you could do the same thing here, and in here, and in here, and in here, and then this guy can transition to himself. Everything can go to S0. So it looks to me like you got to have 8 inputs and 8 outputs for each state. And so the question is, what is the minimum and maximum number of transition arrows starting at a particular state? And so you got to have 8 ins and 8 outs. So you're going to have, let's see if I got the answer right. A minimum for each node will have 8, and a maximum number of outgoing transitions is also 8. And so that's one of the answers. And if you look at over here, certainly he says that's true. So you'd have to have 1 transition arrow for each value. And since you have 3 bits, there are 8 different values. And so they can transition in and out, in and out. And so that's your answer for 8. And it doesn't look like in the chat we have anybody else asking any questions. So, whoop, can we do question 2? Wow, okay. Question 2. I think we did question 2 last time, didn't we? Can we do question 1? Well, we did question 1 last time too. We did both of those questions before. I don't wish to be difficult or anything, but if you like, you can review the recorded session from last time if that's okay. But in fact, we did do these in our prior section, so I don't think I should do them twice. Besides, they weren't that hard. Can we do 17? Can we do 13? Can we do 17 and 13? Okay, so 17 says a flex sensor can be used to create a variable resistor. And the answer is yes. Yes, it can. Here's the flex sensor right in through here. And one thing you can do, if you're ever wondering about something like that, is you can Google these things. But that is an interesting kind of sensor. I actually have one of these. You can bend it, and it will give you a different resistance as you bend it. So what you can do is you can take these things and mount them to the fingers of a glove, and then when you move the glove, it will tell you how much each finger is moving. And so you can use that for an interesting input device, like a VR input device. So yeah, that gives you a variable resistor input. And I would give you a demo of that, but last time I handed it around in class, they broke it, and I haven't gotten around to fixing it yet, which is kind of a bummer actually. But yes, these things do give you a variable resistance when you flex them, and that's an interesting kind of input device. Someone says, can we do question 13? Question 13. Question 13. Question 13 says, Mealy machines tend to have fewer states, different outputs on arcs, asynchronous output changes. So herein lies the interesting thing about Mealy machines, right? We have the combinational logic block, and we have these states. I'll call it state register. And now we have more combinational logic, and it is a function of the state register and the input. And the state register feeds back into the combinational logic, and the input feeds into the combinational logic for input. This is combinational logic for output. This is for input. And now we've got the Mealy machine from George Mealy. And so now the question is, can you have fewer states? And the answer is yes, you can. It actually gives you the ability to save a flip-flop or two, depending on the size of the machine. Can you have different outputs on the arcs? Yes, outputs are related to the arcs, right? So if you look at I'm just making this up. So now we've got a yeah, there it's better. So now we've got an output that's related to the arc, right? So there's the outputs right here on the bottom. Then it says you can have asynchronous output changes, and that's true because this input can propagate through to the combinational logic and give you an output that changes with the input without regard to clocks on the state register, because these state registers are clocked. And since it doesn't have any regard for the clock, when it changes the output in response to combinational logic block input, we say that it is asynchronous. So that's also true. So with 13, it's all of the above. Someone said, let's do question 12. Okay. I'm going to just plop that right in front of the camera here so you can see it. What will be the output sequence if the input is equal to 1? Well, let's see. If you're in state 0 and you get a 1, you go to 2. then from 2 you go to 3, and from 3 you go to 1, and then from 1 you go back to 0. So it looks like it's 0, 2, 3, 1, 0. Or you could write this in any particular order. It doesn't matter. You could start with 1 and go 1, 0, 2, 3. Or you could start with 3 and go 3, 1, 0, 2, 3. So any of those works fine. It's a bit of a peculiar count, but there it is. So it's kind of a down counter, only these are weird numbers in their order. So that's, let's see, what does he say? One of the answers is 2, 3, 1, 0, and that's certainly correct. So if you wrote 2, 3, 1, 0, because it doesn't matter where you start, it's still a legitimate count. So that's an answer. Someone said, can you do question 12? We did that. And can we do question 9? Are there any questions we didn't do in this homework? I was like, I think we did every question. Question 9. So someone says, Moore machines. Suppose you were told a Moore machine has 5 flip-flops and 3 inputs and 9 outputs. Didn't we just do this? This sounds familiar. What are the minimum and maximum number of transition arrows that can end in a particular state? So could it be 255, 220, 125, or none of the above? And none of the above is obviously right because the answer, as we saw in a prior question, was 8 for both inputs and outputs. So I think that was an easy one. Can we do question 14? Okay, we're going to do every question. I'm going to do every question. Let's see what we got. Okay, so here it asks, which of the below is a Moore machine? So Moore machines have outputs which correspond to the arcs instead of just the states. Right? So when we look at something like this over here, we can see that this is, Mealy machines have outputs which correspond to the arcs. Moore machines have correspondence only to the states. So if we're in state B, the only output we have to care about is 0. When we're state A, the only output we see is 0. So that looks like a Moore machine. Now let's look at some of the other machines. Okay. What about this one? Well, this one has no asynchronous transmission between the input and the output, so it too is a Moore machine. That's a Moore machine, synchronous. Right? Because why? Because we have a state register, and the clock causes a synchronous change to the output. So output's only a function of present state. And what's the next one say? The next one has a detail, and this comes right out of the book. Combinational logic. Here's a register. More combinational logic. In fact, this is a detailed version of that. So all of the above. They're all Moore machines. And I guess we did them all now. So now you've got a good handle on on homework 10, I hope. And what I really wanted to do was homework 11, because that's the tough one. And I think at this point we're going to need a fresh piece of paper. So let's do that, because I got to start fresh. Here's a nice fresh piece of paper. So now we're going to go into the world of Chapter 9, and that is finite state machine. And I'm just going to write FSM for finite state machine minimization. And there's two primary ways that the book describes. The first one is called row reduction, and the second one is called implication tables. And both of these appear in the homework. And in fact, both are relatively important from the point of view of trying to get some of these questions answered. And so you need to know how to do both. And so let's see if we can't grab one of the examples out of the homework here. Okay. Let's do a row matching technique. I am going to switch pens. Here's a nice pen. This one will make life a little easier for you to read. And this is going to be row matching. There, how's that for visibility? That's good. So what we'll do is we'll establish the present state, the next state, and then the output. And for the present state, we'll use states A, B, C, and D. And for the next state, we'll use the function of the input, x equals 0 or x equal 1. And then what we'll do is we'll write out D and CCAC. And then in the output, 0, 0, 0, 1. And that is our given. And I'm taking a little bit of a shortcut here. I'm not showing you the finite state machine diagram because it takes a while to draw those things and it doesn't really add to the discussion. And so what you want to do is you want to see if you can reduce this present state next state table before you go to an implementation, because if you can reduce the spec going into the implementation, it will simplify the implementation. Did somebody just write, could we do 20 in homework 11? Well, I think we better learn how to do row matching first. But we will get there. So you'll have to hold your suspense. Let's not jump into the hardest thing, really. So what I'm going to do is I'm switching colors now. And I'm going to come up with some rules. If the outputs are different, then the rows are different. They're not equivalent states. So state A is not equivalent to state B because the outputs are different. B is not equivalent to D. C is not equivalent to D. But maybe A is equivalent to B, and it is because the outputs are the same and the next states are the same. So what you do is you say, let's change the color in here so you can see what's going on. You say that A is equivalent to B. I can get equivalent behavior from the overall finite state machine by crossing out B, and anywhere I see a B, I substitute A. But I don't see B in here anywhere, so it seems like a dead state. I don't need it. So now I can compare A to C. Doesn't seem like A is equal to C. Well, let's see now. I can compare nothing else to anything else. So all I have is A equals B, and that's sufficient. And that's row matching. And that's a simplification. Then there's another way to go. And this is called the implication table. Let's switch back to black color. And at the implication table, you start with the second letter and end with the last, B, C, D. And then you start with the first letter and end with the second to last. A, B, C. And then what you do is you make a lower triangular matrix. And now you have to look at outputs that are different, and if the outputs are different, you put in an X. So A is different from D because A has a different output from D. So I put an X between A and D. B is different from D because B has a different output from D. So I put an X over in here. C is different from D because they have different outputs. So I put an X right over here. Now, let's take a look. A is equal to B if D equals D and C equals C. So that's true. A is equal to C if D equals D and if C equals A. So, in other words, if A equals C, A will equal C if C equals A, and so they are self-referential. So that's true. Now it says here, B equals C if D equals D and if C equals A. Well, we already know C equals A, so that's true. So now we've got a little extra simplification. We have A is equal or equivalent to C, and we have A is equivalent to B, and then we have B is equivalent to C, and if A is equivalent to B and B is equivalent to C, then A is equivalent to C, which is equivalent to B. So now I can take the C part and I can wipe it out, and everywhere I see C I can write A. And that gives us a big simplification. And now we're down to just two different states for this entire system, which is kind of cool. And that is a real nice simplification. You couldn't get it from row matching, but you're able to get it from the implication table. And these are the two basic kinds of state minimization that you can get from chapter 9. Sure. When you're doing comparisons that are pairwise, you don't want to compare A to A, and you don't want to compare B to B. So you're getting the lower triangular matrix. If you had the full matrix, A, B, C, and D, A, B, C, and D, right? You're comparing A to A, right? So in other words, why would you compare A to A? You already know A is equal to A. So the whole main diagonal is excluded. So I don't really want to compare A to A or B to B or C to C or D to D. Moreover, if I'm going to compare A to B, then I don't need to compare B to A, right? Because that's already done. So that's already done. I don't need B to C to A because I already have A to C. So that's already done. These equivalencies are two-way, right? So the whole upper triangle is redundant, right? Because I don't need to compare D to A if I'm comparing A to D. If I know A is equal to D, then D must be equal to A. So this whole upper triangular matrix is removed, and everything below the main diagonal, that's the main diagonal, is retained. And so these are the only comparisons that I need to care about, and the others are simply redundant. What do you think of that? Is that a good explanation? Then it says, is that D or is it 0? That's a D. Sorry for my handwriting. Is there another question? Oh, can we do 20 in homework 11? I'm convinced that if we do 20, we're going to confuse everybody because we just saw like the first implication table, which, you know, was not a particularly obvious thing. So maybe it would make sense to do another reasonably simple example before we go diving into these interesting and wonderful examples that we have in the homework. Well, let me just make sure everybody kind of understands this. I'm going to do another question because I think you have to do a few examples to get it. Get a fresh piece of paper here. Okay. So now I'm going to do a rather more complicated example. We have the present state, the next state, and then we'll have the output. And once again, I'm not going to show the full finite state machine diagram because it gets a little tedious to draw that out. And now for the present state, we're going to number or label the states A through G. So it's A, B, C, D, E, F, G. And then for the next state, which is a function of the input, and I've got to put a little box around all of this. We're going to write out A, B, C, D, A, D, E, F, A, F, G, F, A, F, with outputs got to do something about the lines here. I just want to keep things lined up nicely if I can. Okay, so now we've got two opportunities here to do our minimization. First might be something like the row reduction technique. So we can compare the next state, AB, against anything else, CD against anything else, AD against anything else, EF against anything else, AF. This AF looks like that AF. The next states are the same. So from a row reduction point of view, I can say that E is equivalent to G. So if E is equivalent to G, then I can go in here, take out G, and write in E everywhere I see G. So that seems to work okay. Now I can go back and do it again. Hey, wait a minute. Look, EF, it looks like D is equivalent to F. So now D is equivalent to F because of that reduction I just did. So now I can go back. I'm changing colors now. And D is equivalent to F, so anywhere I see F, I'm going to write D. That's okay. I guess we can do that. And then I can look again. I could say, hey, wait a minute. Here's AD, and here's AD. Aren't they equivalent? And the answer is no. And why? Because the outputs are different. So we have to stop now. How about CD? We don't have anything. AD, nothing. ED, got nothing. So now we've got a nice reduced form. And it's pretty good, but maybe there's more. So I've already done some simplified row reduction technique. Now I'm going to do the implication table. So let's do the implication table starting from the reduced finite state machine table. And so now I've got B, C, D, and E on one side. I only go up to E. Now I'm going to start with A and go B, C, D. And now I'll do my lower triangular matrix. And now I'm going to do my comparisons with outputs. A must be different from D and E because the outputs are different. So I put an X in there. B must be different from D and E. C must be different from D and E. D might not be different from E. So we've got some trivial reductions already. Now let's compare A and B. A and B are equivalent if A equals C. It's equivalent if B is equal to D, but B is not equal to D, so we can cross it out right away. A is equivalent to C. A is equivalent to C if A is equivalent to A, that's good, and if B is equivalent to D. But we know B is not equivalent to D because there's an X here, so that gets X'd out. So now we compare B and C. B is equivalent to C if A is equivalent to C, but we see it's not. And what about D and E? Well, D is equivalent to E if E is equivalent to A, but we see it's not. And so there are no further reductions available. I wondered about B being equivalent to C. We know B is equivalent to C if A is equivalent to C, but we know it's not. So at some level we don't have any further reductions available to us. And so now we have a proven minimized finite state machine, which is cool. What do you think of that technique? Are people sort of getting it? Is that a D or a 0 under next state? These are all D's. That's D's under next state. And these are all zeros under output. Outputs are either 0 or 1. Next states are all letters. Any other questions there? Okay. So that's a that was a good example, I think. Let's do, and I'm going to get to 20. Let's do question 17 because I think it's a reasonably small question and we can handle that with relative ease. I'm going to do it on the same piece of paper over here. So we'll have present state, next state, and output. And then what we'll do is we'll write for the present state A, B, C, and D. And this is going to be question 17 from homework 11. And so now we're going to get to the next state, and that's going to be for x equals 0 and x equal to 1, and an output which is not going to be a function of the actual input. So we'll just write in here D and C. I think we just did this one. Yeah, we just did this one. Sorry about that. That was that one with we did, the one over in here. That was question number, oops, get this out of the way. This was question 17. Let's try question 11 since that seems to be one that's bothering people. So question 11. We'll have a present state, next state, and an output. And I'm going to encode the diagram into a table. So we'll say x equals 0, x equals 1, and x equals 0, x equals 1 for the output. And so for the present state, we're going to number things, label things, A through G. So it'll be A, B, C, D, E, F, and G. And then for the next state, we're going to have EG, DF, EC, BF, GF, BD, GC with outputs 0, 1, 0, 1, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0. And so what you do in order to get something like that is you have to actually look at the diagram and see if you can extract the present state, next state table out of it. And hopefully you can do that. You can read a finite state machine diagram at this point. I'm going to see if I can find question 20 here in the oh, I see it. Right. There it is. I'm just going to bring up question 20. Yeah. Question 20 is not a particularly easy question. Let me see if I can just use this. See, the trouble with question 20 is it's a fairly involved diagram, and I just assume not redraw the diagram here. But this captures all the information that's in that diagram. And what he says is, given the state diagram, choose the minimized state transition table. Doesn't tell you how, but take my word for it, you're going to end up with an implication chart eventually. So we'll start by creating an implication chart. B, C, D, E, F, G, A, B, C, D, E, F. And now I can see that A is not equal to C, F, or G. That B is not equal to C, F, or G. That C is not equal to D or E. That D is not equal to F or G. That E is not equal to F or G, and that F might be equal to G. We don't know. So right away I got rid of the trivial output differences in the rows. Is everybody following along so far? So this is question 20 and homework 11. So, what do we do? Let's see. A is equal to B if E equals D, and if G equals F. Does E equal D? Let's see. We don't know. What about G and F? Does G equal F? So let's take a look. G and F, we don't know. How about we go and explore E and D? So E is equal to D if B equals G. So E is equal to D if B is equal to G. And we can see B does not equal G. That's already been eliminated, so that gets eliminated, which means ED is eliminated, which means this is eliminated. And that's how you quickly eliminate something. You go and do a deep dive into the thing it requires. Let's look at A and D. A is equal to D if B equals E. and A is equal to D if F is equal to G. We don't know about F and G, and we don't know about B and E. So let's look at B and E. B is equal to E if D is equal to G. But we know B is not equal to G. D is not equal to G. B is not equal to E. So we can eliminate a whole bunch of things there. Let's look again. A and E. A is equal to E if E is equal to G. E is not equal to G, so that's gone. C is equal to F if B is equal to E. B is not equal to E, so C can't be equal to F. B is equal to D. I'm going to skip that one. B is equal to D if B equals D. That's good. And if F equals F. Oh, so there we go. B is equal to D. That's a good one. C is equal to G if E is equal to G, but we know it's not. F is equal to G if B is equal to G, and we know it's not. So the only reduction we have is that B equals D. Let's go back and take a look at C and G. So C is equal to G if E is equal to G, and we know it's not. So yeah, this is our minimization. Let's take a look and see what we can do about that. If D is equal to B, then I can remove D, and everywhere I see a D, I can write B. And that is our reduced finite state machine diagram. Homework 20, number 11. Let's see. Someone writes, is that D or a 0 under next state? I think that was from an old question. Let's try a different one. I'm going to go for question 21. So I'm doing a deep dive into some of the harder questions. Let's see if we can do this one. Question 21. This is which time do we have left? Yeah, we have enough time for this one. So this is question 21 from homework 11. So now we got present state, next state, and we got the output. Let's see what we got here. X equals 0, X equals 1, and the output for X equals 0 and X equals 1. And right away I can tell this is a Mealy machine because its outputs appear to be a function not just of what the state you're in, but also of the inputs. And well, this is a long one because it's A, B, C, D, E, F, G, H, I. So let's do that. A, B, C, D, E, F, G, H, I. And this is, again, a rather complicated looking diagram. I don't want to try and draw this. I'm just going to encode it into a table. And I'll leave it to you guys to figure out how to draw diagrams and turn them into tables, because that's pretty easy. It just takes a little while. So that should say AEG EFH HGA, and then it should say CDD BG, sorry, DBG BIIIIII. And there should be 3 zeros at the end, 2 zeros in the middle, and then all zeros. Yep, that's correct. I just want to make sure I transcribe this correctly. Can you look at the diagram and see how I got that? Is anybody confused by this? So if not, I'm just going to proceed. So to start, we need to create our implication chart, which means we're going to be numbering from B, or labeling from B to I, and then from A to H. Right? So it takes a little time. Let's do this. I'll write it off on the side over here. So it will start with B. B, C, D, E, F, G, H, I. Then we'll start with A. A, B, C, D, E, F, G, H. And we stop before we get to I. And then we draw our lower triangular matrix. I'm trying to keep it neat now, but I guess I got messed up. Maybe I shouldn't use these graph pages with the small squares because it makes it too small. There. Did I do that right? I guess it looks okay. So now we're going to take a look and see where we can do trivial eliminations. A must be different from G, H, and I. B must be different from G, H, and I. C must be different from G, H, and I. D must be different from G, H, and I. E must be different from G, H, and I. Actually, we'll keep going. F must be different from G, H, and I. A is also different from C because they have different outputs. What else is A different from? It's different from F because they have different outputs. B is different from C and F. C must be different from D, E, D has to be different from F. E must be different from F. And G and H could be the same. G and I could be the same. H and I could be the same. So we've basically put a lot of X's in all over the place. A lot of X's. This is kind of interesting. Let's take a look at A and B. So A and B are going to be the same if A equals E and if C equals D. Does C equal D? No. So that can't be right. A is equal to D if A equals E and if B equals C, but we know B doesn't equal C, so that can't be right. A equals E if A equals F. A doesn't equal F, so that can't be right. B equals D if E equals E, well that's true, and if B equals D. So that's cool. So B is equivalent to D. That's great. Love to know about certain equivalencies. Let's take a look at B and E. B is equal to E if E equals F. Here's E. There's F. It's got an X in it, so that's no good. C is equivalent to F. C is equivalent to F if G is equivalent to H. Here's G. There's H. We don't know about that. And if B is equivalent to D. Oh, so really we know B is equivalent to D. We're looking at C equivalency to F, and we want to see if G is equivalent to H. So let's do a deep dive into G equivalency to H. G is equivalent to H if G is equivalent to H, and if I is equal to I. Hey! So that's good, and that means this is good. So now I have G is equivalent to H, and I have C is equivalent to F. So those are all good matches right there. Let's take a look at some more. How about G and I? Isn't this fun? So now we have A equivalent to H, which it's not, so that goes. And we'll look at H and I. If G is equivalent to A, and we see that G is not equivalent to A, so that goes. So this is what we're left with. What does that mean to me? Well, it means I can cross out, I'll start from the bottom and work my way up. I can cross out H. Where would that be? Oh, yeah, look, D. There is one left. Whoa, how about that? Thank you. Is D equivalent to E? So let's take a look. Is E equivalent to F? No. So that's it. There. No more squares. All done. So I was just about to wipe out H, and everywhere I found an H, I was going to put in a G. And then I was going to wipe out F, and everywhere I found an F, I was going to put in a C. And then I'm going to wipe out D, and everywhere I found a D, I was going to put in a B. And now I have a reduced finite state machine, and that is your answer to 21. What do you think of that? Pretty cool, right? Now, who got confused by what I've been doing here? I'm not seeing anything in the chat menu. Is it okay if we go on to 22? Because I'm doing the hard ones. And you guys can do the easy ones. I'll do the hard ones. And in the process of doing the hard ones, I think you're going to be learning how this is done. And you have to see it, no doubt. But then you got to try it too. So please be sure to try these things. It's kind of important that you try it. Can you explain again how you get the output? This output here? That output comes from the finite state machine diagram. So if you have homework number 11 in front of you, and you turn to question 22, here's an example. This is from question 20. It's a simpler example. So here's the finite state machine diagram. Now here you can see A has an output of 1 if the input is 1 and you're in state A, and the output is 0 and if the input is 0 and you're in state A. So then what you do is you go over here and you say, okay, here's state A, right? If I put in a 1, My next state is going to be G, and you can see the G over here. The output, when you put in a 1, is going to be a 1, so you put the output 1 right there. And go to the next line in this Mishigas. You put in a 0 when you're in state A, and your next state is going to be E. Your output is going to be a 0. So the top part, that's the input. The bottom part, that's the output. And this arrow shows you what the next state is going to be. And because it's a Mealy machine, you have to have the outputs written alongside of the next states, because the outputs are a function not just of the present state, but also of the input. So you got to know what the input is, and that's why we write the inputs up in here. Does that make it clear? I joined late due to a test, so I'm a bit confused, but I can rewatch the video. Where can I find the video? I'm going to put it up on my webpage, docjava.com, which has a URL that's right here. So I'll be putting up a recording, and I've already got 1 hour and 6 minutes into this thing, and if you joined late, you missed 1 hour of lecture, so that's kind of real late, actually. Somebody told me they didn't even get their midterms yet, and I'm like, man, it's already the first week of April. What happened? You know, they extended the deadline for taxes, but as far as I know, they did not extend the deadline for the end of the semester. So it is going to happen. The semester will end. Yay! I mean, this was not an easy semester. But we're doing the best we can. So there you go. So last time we did we do question 22? No, not yet. Let's do question 22. Do we have time for question 22? Yeah, maybe. This is another big question. Okay. Let's see if we can move on and try and get question 22. Question 22. Yeah, this is, somebody said they're confused because they came in late, and my answer to that is, this is the most challenging chapter that we have done so far, and a lot of people get confused by it. Now bear with me a minute while I try and adjust my my focus, because I don't think this is as focused as it should be. All right, that's all right. So this is going to be question 22 from homework 11, and if we don't finish it, we're going to pick it up where we left off from last time. We have 6 minutes, 5 minutes, 45 seconds. I do not want to rush this question. I'm sort of sitting here looking at it and going, that's a lot of writing to do, and we're not going to finish this. I don't want to start a big question that I know I can't finish. That doesn't make sense. Let's do a simple question. I'll do a couple of simple ones. I think that's better. So here's an interesting thing. If you look at the you're gonna love this. This is what a dollar looks like from the 1860s. This is $1839. And in fact, the size of these dollars did not change right up until they had silver dollar bills that they were issuing around the turn of the century. Herman Hollerith, interestingly enough, decided that he would create punch cards that were the same size as the dollar because he wanted to use dollar sorters in order to be able to help sort the punch cards. And so he created a standard for punch cards that basically lasted well over 100 years. And here's another one from the Bull's Head Bank. And in fact, all of the bills of the day were very large. And so the punch cards of the day became very large. And in fact, let's see if I can pull one out for you. I have here a real-life punch card. And so what he did was he used spring-loaded pins that would come down on top of the punch cards and make contact if there was a hole with a little cup filled with mercury. And apparently nobody cared about messing around with mercury, even though it's known that it's not really good for you because it dissolves neural tissue and it has a half-life in the body of 70 days. But be that as it may, the question that we have to face is, and here's the man in question, Herman Hollerith. Punch cards got their size because of the size of $1, and yeah, $1 at the time was a big piece of paper, big note of liability from the local bank. And the further you got from the local bank, the less it was worth, because you had to go back to the local bank to redeem it. And so we didn't have a national currency at the time, and so this is kind of, every bank had its own currency. Imagine that. So that's where Herman Hollerith got the idea for the punch card, which is kind of an interesting thing. And then we had a little video, which I encourage everybody to watch, about the tabulating machine. And that tabulating machine gave birth to a computer industry. IBM bought the Computating, Tabulating, and Recording Company. That was by Watson. And then eventually they became IBM. And they standardized on the punch card. So that was a machine that was electric, not electronic. So when you go to question 3, they ask you, was the tabulator an electric or an electronic machine? The answer is it's electric, and it's not electronic. There's no tubes, there's no transistors. These things were invented before tubes and before transistors, and they didn't have relays either. They were basically just electric devices. Then the next question is, and this is, I'm doing the simple questions because we don't have much time. It's about the Thunderbird. And I don't know if you've seen this video. This is kind of a cool video. Let me see if I can bring that up for you. So here is a Thunderbird, and check out what happens when you turn, right? It goes through a sequence. That's kind of cool, right? This was on a final. And so this is a finite state machine, and they implemented this with relays inside of the car because they wanted it to be able to do all of these features. And so you can see the sequence of lights that are going through when you do a left-hand turn and a right-hand turn. I don't know if you're car people or not, but even if you're not, that's pretty cool. You don't normally see that in cars. That's kind of neat. And of course, you could have done it with like a little microcontroller, like an Arduino or something or other, but they didn't have that then. So that was the Thunderbird, which is pretty cool, I think. So that's what I have for you for today. I'm afraid we don't have any more time for anything else, but thank you very much for your attention, and we will see you on Thursday. Thanks a bunch. Stay safe. Bye-bye.